Hello students, you all are warmly welcome to our YouTube channel Chemistry Teacher. Here in this lesson, we are going to present you about another topic found in organic chemistry. As in earlier two videos, I'm going to extend that topic. Students, it's the monosubstituted products of benzene what we are going to talk here about. In earlier videos, we found that out. When you have a group attached on benzene ring straightly, we call that when it is one group attached a monosubstituted product. Normally, when you look at the reaction standing for benzene, benzene is quite different than other normal unsaturated compounds. Alkenes, alkynes are unsaturated compounds, but benzene is in between of saturation and unsaturation. It's quite a stable structure compound than normal unsaturated substances. Therefore, while other unsaturated substances like alkenes and alkynes were participating in electrophilic addition reactions, it's benzene you could find out involved in electrophilic substitution reaction. So it's a specific kind of reaction that benzene have. Benzene is famous at. Okay, students, then it's about that we are going to find that out when benzene ring is exhibiting such electrophilic substitution reaction. Those electrophiles which have the thirst for electrons, which have less electron densities, which are positively charged, would get attracted towards the benzene ring seeing a rich electron cloud or high electron density with benzene. So then, if the group attached on benzene, if it increases the electron, this is the benzene, this is the group attached on benzene. If it increases the electron density on benzene, then it makes benzene's reactivity high. So it could then benzene with a great electron density could attract those electrophiles towards that. So if it reduces the electron density finally on benzene, then the affinity or ability of benzene to attract those electrophiles towards benzene itself would be low. Therefore, based on its ability of giving increasing electron density on benzene as well as decreasing the electron density on benzene, we name it as either activated group or deactivated group. If we looked at that fact, they are in our earlier lessons. Okay. Then it's further. When the electrophile is coming, so seeing some electron density on benzene ring, it would get attracted. Seeing some extra negative charges somewhere, the electrophile coming would get attracted towards that position more. So based on that fact, we earlier found out some of these groups attaching on benzene increase the electron density at Otho-para position for some times, comparatively maintained electron density greater at meta position than Otho-para positions. It's then electrophile more likely attached at Otho-para positions for some times and for some other times at meta positions. So based on that, we name such as Otho-para directing groups when this group is doing such a thing, as well as meta directing group. We talk about such skills, such specifications regarding benzene that affecting inserting by these groups attached to benzene based on two impacts. One was the resonance effect. The other was the inductive effect. So, then based on such two, we talked about so far we have talked about so far. The groups, when you have a OH group here, it's we call phenol. When you have a NH2 group here, it's we call aniline. When you have a nitro NO2 group here, it's we call nitrobenzene. Then when you have OCH3 group there, it's we call anisole. Then when you have a Cl group there, it's we call chlorobenzene. Those we have found out, we have talked about. Then students, here in this lesson is our effort put on benzene's ring, benzene's substituted group. When you get it's let's talk about an aldehyde group attached on benzene once. Then finally we'll talk about a methyl group, alkyl group attached to the benzene. So then it's respectively we could call them benzaldehyde and toluene. Okay, let's find them out how those aldehyde groups and methyl groups act on benzene, getting attached to benzene, how it either increase or decrease the electron density on benzene, as well as how it directs, how it leads coming electrophile to various positions. Okay, so it's our major focus is now on aldehyde. Let's find it out. What would it happen there when you get benzaldehyde, means an aldehyde group attached to the benzene? Students, it's very easy. This is the aldehyde group. Okay, it's you have two lone pairs on oxygen atom. Then, talking about the impact of aldehyde group on benzene there, it's we need to talk about once the resonance effect. Let's talk about, it's the time. So it's the resonance effect. So talking about the resonance effect, we need to draw resonance structures that aldehyde group involved. I'm going to start drawing that. Students, when you start drawing such resonance structures, I have already told you what to do first. If you find the atom that's straightly attached to benzene ring is carrying a lone pair, you need to start resonation giving that lone pair towards benzene ring as to form a pi bond between that atom and benzene's carbon. That's how you need to start when you have a lone pair here on the atom that's straightly attached to benzene ring. Otherwise, it's here you don't have such. You don't have a lone pair. Then if it is the case situation, then further if you have a double or triple bond on that atom formed with another atom more electronegative. So you start showing the resonation breaking that pi bond on the other atom. Is what we are having here in this benzaldehyde. So let me show you that. Students, its resonation starts here, breaking this pi bond, giving a lone pair of oxygen. So it starts. Then the number of bonds get reduced to 3. So to avoid that, this pi bond breaks there, forming. Then its 2 electron is used to form a new pi bond between this carbon and benzene's carbon. Students, what you get next is, we are doing this arrow to denote that it's a resonation and resonance structure. Next, what you are having. So students, what you are now having is, you have a double bond here with this carbon and H, and it's a single bond. It has become a single bond. The pair equals there in lone pair. You now have there as a lone pair on oxygen. So it's negatively charged. So students, this pi bond is still there, this also unaffected, but this pi bond is no longer there, but here forming the pi bond between this carbon and this carbon. So this pi bond, regarding that, when I say further things, that pi bond has been formed between this and these two carbons. Each carbon has given 1 electron on that formation of pi bond. But both electrons are now there between these two carbons. This carbon remains unaffected, but this carbon has lost its 1 electron. So it's a positive charge you get there on that carbon. Okay, that's the resonance structure. Students, next, it keep resonating. So this pi bond breaks as to form a new pi bond there. So we denote it with this arrow, curvy arrow. It's next. What I could show is, students, this pi bond remains unaffected. This double bond is still there, and this is there. This is a single bond with 3 lone pairs. The negative charge is still there. Then, with the formation of this pi bond with these 2 electrons, between these 2 carbons, now you have another pair, K. So with that, this negative charge gets neutralized. This positive charge gets neutralized. Then students, there were 2 electrons in this pi bond. Those 2 electrons only were given here. So then those 2 electrons were kept between these 2 carbons as each has given 1 electron there. So what has happened now is this electron has lost its electron. So this carbon has lost its electron. So students, it remains a positive charge there. Means it newly occupies a positive charge there. Okay. Then it's again ready to resonate. So this pi bond would break here, forming a new pi bond between those 2 carbons. Then with that, this positive charge would get neutralized, but the positive charge would reappear here at this carbon, on this carbon. So then it's you get the next resonance structure having this double bond and the double bond here, and it's 2 single bonds. This is 3 lone pairs. It's negative charge. So you get the new pi bond here being formed, and this would become a positive charge. After losing this carbon, after losing its 1 electron invested on formation of that pi bond. Okay, then students, what you will get next is further resonation. So this pi bond breaks here, and then one of those lone pair would be using to form a new pi bond here. So you get the structure back. It's the last resonance structure I will give is this. So it's you get a similar one as it was earlier. Okay, this is the resonation, and these are the 5 resonance structures formed during resonation. Okay, then students, when you check for those resonance structures, so it's taken off electron from benzene. Here you would see. So within these 3 structures, it's a positive charge is maintained on benzene. It indicates, it says that it's a positive charge you have on benzene. Therefore, it lacks 1 electron on benzene. Therefore, its electron density has been affected. It has been reduced. It has been lowered. This then is not giving electrons towards benzene, this aldehyde group. It's taking electron from benzene. It's a negative resonance effect. We call such effects are negative. Negative resonance effect you get there. Then what about the induction effect or inductive effect? Students, when you check for induction or inductive, let's call it inductive effect, it's we need to just check for the benzene's carbon and the other carbon that you find the aldehyde group there. So I'll draw it here in this way. So then it's both are 2 carbons. Therefore, it's you would say that it's no resonance, no induction effect. Means induction effect is nothing else but between those 2 atoms, when you find an electronegativity difference, the more electronegative atom would draw the electron cloud of the sigma bond. Then students, regarding this sigma bond, both carbons are equally electronegative, but this carbon is slightly more electronegative for the reason it has got this oxygen atom attached to that. It is highly electronegative. Therefore, it draws the electron density, making its positive on this carbon. So if this carbon then tends to attract electron more towards that. But for the reason it's those two atoms are belong to same element, so let's say it's no electronegativity, such significant electronegativity difference. It's no induction effect, inductive effect. Then you have a negative resonance but no induction effect, significant induction effect. Therefore, students, it's finally this expresses the total character of benzene. What the character they are? Compared to normal benzene, now the electron density is less there in benzaldehyde. Therefore, it's a deactivated group. This aldehyde group reduces the electron density on benzene. Therefore, it's a deactivated group of benzene. Therefore, it's less, the reactivity of benzaldehyde benzene is less compared to normal benzene when they react with an electrophile. When the benzene ring is attacked by an electrophile, it's normal, just benzene is more reactive compared to benzaldehyde. Okay, so then students, now our concern is we found that out, the fact that the CHO group, or let's call it aldehyde group, is a deactivated group of benzene. Now our concern is, okay, if though it's deactivated group, still it's possible those electrophiles to come and get attached. So now our concern is where those electrophiles would more likely get attached. Is that all the positions, all 5 positions equally attacked and attached, or it's differently, means more likely one position or few positions are attacked while others are not. Okay, let's find it out. When you check for these resonance structures, it's electrophiles are positive species which allow negative sites, more electrons, high electron densities. Then, in such a situation, coming electrophile would not select, would not choose a place that you have already positive charge, because electrophile itself is a positive charge or positively charged species or electrodeficient species. These electrophiles, they love electrons, that's why we name them as electrophiles. Then those won't attach and attack to those positions where you have less electron densities, where you have positive charges. So this place is the Otho place would not be attacked that readily. So as well as this place is a para place, would not be attacked that easily, that lightly. As well as again these Otho positions. Then they are skipping, they are missing those Otho and para positions. Then compared to those positions with positive charges, it's no charge you see here at the meta position. In any resonance structure, there is no charge you could find there. Then rather than positive, its no charge is better. Compared to positive site, no charge sites are highly electron dense areas. Therefore, coming electrophile would select this no charge, these meta sites. Therefore, students, I could call this the aldehyde group here of benzaldehyde is directing the coming electrophiles. You get attached to meta position. It's useless getting attached to all the positions and para positions because you are a positively charged species. Those positions or those places also are positively charged. Then students, it's a meta-directing group. That's what we have got towards you regarding benzaldehyde. Okay. Now student, we are ready to talk about our second substance. As I have promised already, we are going to now talk about the substance toluene. Let's find it out. Toluene, how would it react, or how would it make, how toluene CH3 group make changes on benzene? Let's find that out. Students, we are going to end this story. And this story means talking about these activator, deactivator groups. There are various capacities to increase the electron density and decrease the electron density. We are going to end that with toluene. It's our last example, but it's more than those already taught examples. We would be having in the working field, in those question papers, we would be having more other groups as well, asking us to determine whether it's an activated group or deactivated group, whether it's an Otho-para directing group or meta-directing group. Okay, finally I am going to brief you all those possible groups to be given there regarding their activation, deactivation, capacity, ability, as well as their Otho-para directing and meta-directing kind of property. Okay, so let's last it with toluene. Students, when you have a methyl group attached to benzene, it's what we call toluene. Okay, then what's the methyl groups? Methyl groups, the alkyl group, impact on benzene? Is that activating or deactivating the benzene ring? Now, we are anyway using those two effects, right? Now, we are going to consider the resonance effect. Resonance effect of the CH3 group on benzene. So, you need to start drawing resonance structures standing for this group, methyl groups, its involvement of resonation towards benzene. Students, as I have told you earlier, that when you have a lone pair on the straightly attached atom to benzene, then you start resonation, giving that lone pair towards benzene ring with an arrow, forming a pi bond. Or otherwise, if you find either double bond, triple bond on that atom straightly attached to benzene, then you start your resonation, breaking that pi bond away the benzene ring. Here, you don't get any such. There are no any such pi electrons to resonate on this methyl group. Therefore, students, here it's no resonance effect you could expect. No resonance effect. So then, as we have experienced earlier, it was no induction effect. Now it is no resonance effect. Then it's our only hope is on the inductive effect. Let's find it out. The inductive effect. Inductive effect. Okay. Students, regarding the inductive effect of toluene, its methyl group, so you could see that both are carbons. It's no such significant electronegativity difference you get between this carbon and this carbon. Therefore, it's at the very beginning, it's a signal like no inductive effect as well. But wait, alkyl groups, when you have this methyl group, it's as the net result of these electronegativity differences. So this methyl group serves as an electro-repelling group. It repels, it pushes electron, it repels electron as it gives an electron pressure towards the benzene's carbon through the sigma bonding. That's what electro-repelling alkyl groups do. Therefore, it's a positive thing. It's towards benzene, it's giving electron through the sigma bonding. So, therefore, it's a positive It's a positive inductive effect. Inductive effect. You could expect there in toluene. Okay. At the end, we have got one effect being positive. Therefore, students, you would expect there in toluene a positive inductive. Therefore, overall effect net result is positive. Therefore, you would expect this methyl group of toluene activating the benzene ring. That's right. Okay, it's an activated group of benzene. Then earlier we talked about its directing ability. As Otho-para directing groups, we found them out. Meta-directing groups, we found such out. So benzaldehyde was a meta-directing, right? So then it's we did observing those resonance structures when they were forming resonance structures. Now here with the toluene, you don't get such a resonance structure that methyl group involved. Therefore, we can't talk about its directing ability with respect to the resonance structures. Then does it mean that it does not direct those coming electrophile any site? Or its coming electrophile equally could get attached to ortho-meta-para positions? Not being biased, not being favored. No, we can't say like that. Students, regarding toluene, what we need to know is, it also is an Otho-para directing group. Without evidences or without such a method as to show that, how could I say such a thing? Okay. We have a method. Anyway, we have a method as to convince you that it's not a meta-directing but Otho-para directing. But now at this time, method is quite different. At earlier times, it was showing the resonance effect, its positions, those carrying more negative sides or negative charges. Then only we told it's Otho-para directing group or meta-directing group. Then we can't do the same here because it's no resonation, it exhibits. Okay, but it's still, we are using another optional way to convince you it's an Otho-para directing group. Students, now it's my effort to show you that. Okay, we consider those moments that toluene involves in reactions. Which reactions? So it's toluene's benzene group is our concern now. So therefore, when the benzene ring here, when the benzene ring is attacked by an electrophile, is what we need to consider here about. So it's not just benzene, it's not toluene. Toluene, when it is attacked by an electrophile, to symbolize the electrophile, it's a positive species at most of the time. So to symbolize that, I have written E. For an example, it could be a Cl plus, it could be a NO2 plus, it could be a CH3 plus, another alkyl group, it could be a acyl group as well. Various such electrophiles could come and attack on benzene ring, seeing a high electron density on benzene ring. So then these are possible electrophiles. Out of those, I will randomly select one of them to show you the reaction, or to prove you that toluene's methyl group is an Otho-para directing group. Okay, let's assume it's the nitration reaction on benzene. So benzene's nitration, students, hope you could still remember, was happened when you treated benzene ring with concentrated HNO3 and concentrated H2SO4, and when you heated that, it's saying that 55 degrees of centigrade. It doesn't matter. When you just heat is enough. So it's, you get a nitro group being attached. Okay, that's what we call the nitration reaction. Students, this nitration reaction follows 3 steps. We talked about, therefore it followed 3 steps. One was the formation of NO2 plus cation, nitronium cation. Second step was the attack of formed nitronium ion on benzene ring. The third was the re-aromatization of benzene ring. Okay, so then it's now we are going to talk about this nitration reaction. We are taking it as just an example. It's therefore I am starting this mechanism from the very second step. What's the very second step? Students, it's the attack of the formed nitronium ion on benzene ring. Okay, this is just the benzene's reaction. Then when same thing is having on what? Toluene. This is toluene. Let's use nitration mixture HNO3, H2SO4, both are concentrated. And when you heat, you would get certain product. It's what our now concern is, where this nitro group get attached. Now it's we are thinking on, is that more likely the Otho position or meta position or para position? So if it is Otho, you get this. If it is meta, you get this. If it is para, you get this. Then it's still, we are not sure. Oh, I'm going to prove you that finally it's Otho-para. It's another thing. Let's not be biased. Let's say still we are not sure whether it's Otho position, meta position, or para position. That nitro group get attached. So then let's treat them equally. Means let's give those each position attacks equal chance on all those positions. Okay. Then let's talk about the mechanism starting from the second step of that nitration. Okay. Here I'm going to do that. Okay. Check this. Students, it's in the second step that already formed NO2 plus would attack. It's if it is the orthonitro product going to be formed compared to CH3 group, if it is orthonitro product is to be formed, this is the nitronium ion. So this should attack on this, but we draw the arrow in this direction to show the flow of electron. So students, what you get next is the orthonitro product, but it's intermediate. In the mechanism, very first what you get is the intermediate. These two pi bonds remain unchanged. So on all those carbons you get hydrogen. So I am showing these two hydrogens only for the reason that I could show you the change taken place. So students, if the nitro group attacks on the carbon here at Otho position, so you get the plus charge here. Then otherwise, if it is to find the meta substituted product, let's say, so this is methyl in toluene. Compared to that position, it is this the position that NO2 get attacked and attached. So then you have H's there, but the positive charge is on this carbon. Then when we talk about para position, I need to use another toluene molecule as to show how is that para position attacked. So similarly, I'm using this pi over here, so I'm going to draw these two H's over there. So when you have nitro group, this is the nitro group. Hope you could see that. So it's you have a positive side, positive charge on nitrogen. So it's going to attack on this pi bond. Means it's going to attack on either this carbon or this carbon. Our concern is on 4, means para position. So we are doing arrow from minus to plus. Okay, if it is the situation, if it's the case, what you get is nitro being attached here. You have a H there, you have a H there as well. So this is methyl group. This remains unchanged. So a positive site there on that carbon. These are the intermediate cations formed by each attack. Why did I draw those intermediate cations? Students, stating you what's the electrophilic substitution reaction basically having on benzene. It's I told you there will be 3 steps followed. First step is the formation of the electrophile. Second step is the attack of the formed electrophile on benzene. Third is the re-aromatization of benzene. So then after the attack of the electrophile on benzene, you would get such an intermediate. Here an intermediate, another intermediate, another intermediate. So it's compared to Otho product, this is the intermediate. So compared to meta product, this is the intermediate. Compared to para product, this is the intermediate. Students, the intermediate would not form if it is not stable, if it is unstable. So explaining that earlier, during the mechanism, I explained that earlier during this electrophilic substitution, formed intermediate follows some resonation. It's called sigma complex. So then it follows it follows the resonation as to form few resonance structures. So let me show you each resonation of each intermediate cation. So when this intermediate cation is about to resonate, this pi bond would break here, forming a new pi bond. So you get the next resonance structure like this. It's now you have a pi bond here. So 2 groups H and NO2. So it's this pi bond remain unchanged. So it's a methyl group you get there. Then the positive charge has transferred on that carbon. Then next, further, the resonation will follow as breaking this pi bond here on its. I will show it there in this way. Breaking that pi bond here as to form a new pi bond. So it's another resonance structure. Students, it's when you get that happened, it's a new pi bond formed here, another was there. So these are H's and NO2s. So it's the methyl. So it makes this carbon on benzene positive. That's the sigma complex formed during the resonation of intermediate cation. They are of the we call Otho attack. When Otho attack happens, then regarding meta attack, then students, the resonation I will show you as it initiates with the breakage of this pi bond here. Then I need to give you a resonance structure standing for that. So it's no longer you get this pi bond, its new pi bond has been formed there. This is the methyl group. So there was an H here, there are NO2 and H here. So it's a double bond. So that positive charge here it was get transferred to the site here on that carbon. Then students, next what it happens is this pi bond breaks on this between those two carbons, forming another resonance structure. So it continues the resonation as now you get new pi bond formed here. There is the pi bond, so it's you have NO2 and H. There, this is the methyl group. So the positive charge transfers on this carbon. This is the sigma complex formed by the intermediate cation in meta attack. Okay, meta substitution. Then regarding para substitution, I could show a similar resonation. Students, it's this 5 breaks here. So I'm about to show the resonance structure. So it's next. This is the CH3 and this 5 bond remains unchanged. So a new 5 bond here formed. You have a H here, you have H and NO2 there. So it get changed. The position of the plus charge was to there on this carbon now. So at the next time, it further resonates, breaking this 5 bond here between the two carbons, forming a new carbon there. So you get another resonance structure. Here a 5 bond, you get a positive charge here. Then it's H and NO2 still, H still, so it's CH3. So these are the 3 resonance structures standing for para attack, para substituted products, intermediate. When it follows para substitution, then the intermediate would exhibit this kind of resonation. So it seems nothing kind of different. It seems still nothing different standing for each resonation. Again, what I am doing is I am going to convince you this methyl group of toluene is an Otho-para directing group but not meta directing group. Okay, students. Doing that, what I did was I started giving you during the electrophilic substitution reaction. There will be 3 steps followed. It's formation of the electrophile, then the attack of the formed electrophile on benzene ring, then the re-aromatization, reformation of the benzene ring. So out of those 3 steps, I am here using the second step. Is the formed electrophile's attack on the benzene ring. It could be various species standing for electrophiles. NO2 plus, Cl plus, it is alkyl plus, it is acyl plus cations. So out of those, I just used for this instance, I could use any of those. Randomly I used NO2 group, NO2 plus group. We call it nitronium ion. Its attack on benzene ring. So not being biased, I have shown you it could attack either Otho position or meta position or para position with respect to this methyl group there. So then what it happens, how we could explain that this is possible, this intermediate cation formation is possible is showing this resonation. It's what we call the sigma complex. This is the resonation followed by the intermediate cation here, standing for the Otho substitution. This is the resonation followed by intermediate cation here, standing for the meta substitution. This is the resonation followed by intermediate cation of para substitution. Okay. Then they all involve in resonation forming 3 resonance structures. Then what's the difference? Okay. Students, we are talking about the involvement of methyl group, intervening of methyl group or impact of methyl group on this intermediate cation stability. So methyl group is an alkyl group. Alkyl groups, they are electro-repelling group. What they are good at is repelling of electrons towards the benzene ring. So therefore students, this is now ready. Our methyl group is ready to repel electrons towards the benzene ring. So it will repel electrons towards the benzene ring, towards the benzene ring, towards the benzene ring. Repelling electrons towards the benzene ring, it will help that ring to neutralize or lessen the positive charge on the ring. So it favors, this methyl group favors on neutralization of favors on that positive charge as reducing its positiveness, making it more stable. Okay, when it does here, it's giving electrons but the positive charge is there. Okay, it's good, but it's not straightly affected. But it's when it is here giving electrons towards the benzene, its positive charge is there. Therefore, it's a help, but that help is not truly kind of straightly fruitful, effective help on this charge. Neutralization of this charge would happen or would be done by this given of electrons, not straightly but indirectly. It's a support anyway. But here in this context, so at this context, it's on this carbon you have the positive charge. Then the support of this methyl group is giving electrons is straightly felt by this carbon. For that carbon, you have got positive charge on that carbon. When there is a methyl group attached on that carbon and giving electron towards that carbon, it's quite like, for that carbon, it's quite like a bliss. Okay, it's a favor. It's a great favor at the moment when you are at a stable situation. Then when someone is straightly helping you, it's a great support. Similarly, it's when you have carbon being held by methyl group straightly, it's a straight support, so it feels much convenient at the time. So students, then here in this resonation, it's you can't find such a positive charge in any resonance structure on that carbon. So therefore, yeah, it's this methyl group also is supporting, it's helping, but this ring cannot take the help straightly on that carbon. It's for the reason not the positive charge is always there, but not on that carbon. So it's kind of a good thing that electron repelling nature of methyl group, it's giving electron towards the benzene ring. It's a good thing regarding anywhere you have in this benzene ring, somewhere you have this positive charge. Therefore, in the context that anyway it's giving some electrons towards me, anyway it's helping me, in that aspect it's okay, it's good. But it's not straightly helping, that giving straightly to the atom that got the positive charge. There is no such positiveness on that carbon you could find here being straightly neutralized. Okay. So then here also you get here on this carbon the positive charge. In one resonance structure again you get a positive charge on the carbon that methyl group has straightly attached. Then in that methyl group would repel electron towards that, neutralizing or reducing its positiveness. Therefore, it's a great support provided by the methyl group than any of here. It's here also you get at this. Therefore, considering these three resonations, its students, this and this resonations are favored more, means stabilized more by the methyl group, alkyl group, giving electrons towards the positively charged carbon straightly. Therefore, these intermediates are more stable compared to this. Therefore, formation of more stable intermediate cation is more favored. Therefore, attack at Otho-para sites, attack and attach of Otho-para sites would be more favored. Therefore, it's finally I'm going to convince you methyl group supports the attack and attach of at ortho position and para position. Therefore, toluene's methyl group is an Otho-para directing group of benzene. That's why. Hope you could understand. It's regarding the intermediate carbocation stability, considering its how this methyl group's electronegative nature is used by the intermediate carbocation. These cations could efficiently use methyl group's support. Though here also methyl group is supporting, this is not lucky enough to get the support straightly. Therefore, these are more stable compared to this. Therefore, formation of these are more favored compared to this. Therefore, attack at the ortho and para sites are more favored compared to meta attack. Therefore, methyl group of toluene is an Otho-para directing group. That's how differently we could explain why and how this CH3 group of toluene is an Otho-para directing group. Hope you would understand. Okay. Then students, I'm going to show you another important thing. I'm now about to brief these all informations that we have found even in our earlier two lessons as well regarding monosubstituted products of benzene. I would explain it in a way like this. Students, this is actually not a chemistry concept. This is not a chemistry theory. This is something else. This is, let's say, an easy way to memorize or something. But we have got pure ideas, pure concepts in chemistry as in the determination of Otho-para directing groups and meta-directing groups. We looked at those resonance structures, resonations. So then in the determination of activator groups and deactivator groups, it will consider resonance effect as well as induction effect. Those two together. Then only we got to say, that it's an activator group of benzene. It's a deactivator group of benzene. So those are the true concepts. But then you could easily find it out. This is not a chemistry kind of theory or concept, right? It's an easy way of finding out whether it's an activator group or deactivator group, as well as whether it's an Otho-para directing or meta-directing group. This is not chemistry anyway. So this is something else, as we would say, it makes easy to memorize those, find them out. So okay, let's find it out what I have got standing for finding out of Otho-para, meta, as well as activating and deactivating groups. Students, if you have a benzene ring that has got an atom here, doesn't matter what is that, an atom here. If this atom is having just single bonds only, doesn't matter what's the number of bonds. If this atom is having single bonds only, or it's no matter, though it's not having any bond, but sometimes it could be having lone pairs. So then these are not meta-directing groups. These all are, at all the times, are Otho-para directing groups. Again, when you find the straightly attached atom on benzene carry just single bonds only or no bonds, then it's an Otho-para directing group. Then students, if that atom which has straightly attached to benzene, so let's say it's D, so if it's having double bond or triple bonds, more than one bond, so then it's a meta-directing group. A meta-directing group. That's right. When you have on the straightly attached atom on benzene, when you have either double or triple bonds, it's a meta-directing group. Then further, all the meta meta-directing groups are deactivated groups of benzene. These all are deactivated groups of benzene. Then further, all the Otho-para directing groups except halobenzene, except chlorobenzene, halobenzene, they are the activated groups. Again, all the meta-directing groups of benzene are deactivated groups of benzene. This is not a theory, this is not chemistry theory. So all the meta-directing groups are deactivated groups and all the Otho-para directing groups are activated groups, but its halobenzene, chlorobenzene such are deactivated groups, though they are Otho-para directing groups. They are Otho-para directing but deactivated groups. All the other Otho-para directing groups are activated groups of benzene. Then students, it's finally I am going to show you all those groups, their relative ability to activate and deactivate the benzene ring. It's the least activator, or let's call it is nitrobenzene, reduces the benzene's electron density very much. It's the least reactive. NO2 makes benzene ring is highly deactivated. So it's the least reactive. So compared to that, if you would find next carboxylic acid, it's the benzoic acid. Compared to that, if you would find next the aldehyde group. Compared to that, if you would find a ketone group. So both aldehyde and ketone groups are having carbonides, but this is a methyl, so it's giving electrons towards carbon, so it's quite greater. It's not that highly deactivated. This is the most, means what we have got in our list. This is the mostly deactivated one, second most, then next, then next. Next you find it's chlorobenzene. It's chlorobenzene. What you have next is just benzene. All these are deactivated groups. Then thereon you get activated groups. It's what you have next is toluene. What you have next is phenol. What you have next is aniline. And what you have being greatest in activity is anisole. So the ability of their or electron density on benzene would be followed in this direction. Ability of their activating character on benzene, electron cloud in the benzene, increasing of electron cloud on the benzene would be greatest here and least here. So after benzene you could find deactivated groups. So thereon after benzene you could find all are activated groups. Then here including chlorobenzene, this is just benzene, so ignore. These others are Otho-para directing groups. These groups are meta-directing groups. That's what the summary of all those, including these 3 lessons. Okay students, those are very easy few points that we have got towards you. Okay, if we are going to continue our lessons regarding organic chemistry with some other conversion reactions involved with organic molecules in our future lessons. Students, till then, if you are going to round up here in this video, so goodbye.